So you open your IDE and you start conversationally explaining what the new feature is and what its requirements are with your AI coding companion. So you go back and forth and exchange some ideas about how you're going to approach the problem, what kinds of libraries you might use, and also what parts of the existing code base you'll have to modify in order to implement the feature. So after a while, you settle on an approach. So you start writing a function in your IDE. And then a few characters in, your AI coding companion comes up with a snippet of code that you could potentially use. And it's exactly what you had in mind anyway. So you adopt the snippet of code. It looks OK, so you go ahead and test and deploy it. Now, after a while, it does work for a while, but as is often the case, your users do something completely unexpected, which ends up breaking your system and causes some errors to appear in your logs. But your AI coding agent autonomously picks up on these error messages. It analyzes the cause of the error, it finds the source of it in the code base, and then it goes ahead and creates a bug fix as well as a pull request that you can review for further integration. So you review the pull request, it looks OK, so you go ahead and test and deploy it again. Then the error disappears, your users are now happy, and then you can move on with the rest of your day. So while parts of this story may sound like a dystopian future that's not quite within our grasp yet, I'm here to show you that the next-gen developer experience and self-healing code is in fact possible already. So today we're going to walk through the life of a day of a developer in the near future who capitalizes on the code generation capabilities of generative AI and how they leverage them both in a proactive and reactive sense in order to enhance their capabilities as developers. So in terms of this session, we're going to start off with the basics of what is a generative AI coding companion and how can you leverage it to enhance your capabilities as a developer to plan and write your code. Then we'll go into the main theme for today, which is building a code-base aware generative AI agent and how you can leverage it to improve your operational capabilities as a developer. And then finally, we'll walk through an end-to-end demo of self-healing code where we're going to see an application bug get fixed in real time autonomously by our self-healing code system. So generative AI is already starting to make a mark in the developer experience. But to be clear, generative AI is here to enhance our capabilities as developers, as well as streamlining our existing workflows. So if we're able to embrace generative AI as a companion in the developer experience, we're going to be able to better understand, plan, and build our applications, and do it at a quicker velocity as well as higher quality as well. So what kinds of activities can we perform already using generative AI as a coding companion? First one is something that you're probably already aware of or are actively using, and that's the idea of code suggestions and code completion. So if you wanted to write a new function in your IDE, for example, you can use a service like Amazon Code Whisperer, which can make code suggestions and code completions in real time within your IDE. And you can also extend that use case out into writing unit tests for your existing code, or even infrastructure as code templates like CloudFormation, YAML. So what if you're new to an entire code base and you wanted some help wrapping your head around the concepts or understanding the code? Then you can use Amazon Q directly in your IDE in order to ask it pointed questions about what particular functions did, or even ask it to explain what the overall code base did in human understandable terms. And then finally, you can even use Amazon Q code transformation, which is currently in preview, in order to perform full language version upgrades. So for example, if you wanted to upgrade from Java 8 to Java 17, you can use Amazon Q to perform the dependency updates as well as the code base updates, and it can present it to you for review for integration. So let's say that we've used all of these different generative AI coding tools in order to collaboratively create and deploy our application to our production environments. What happens when inevitably our users come along and break our system in ways that we didn't even think was possible? And that's despite our best efforts to shift all of our development practices to the left as far as possible to detect issues in security and performance and user experience as early as possible. So clearly, there's always going to be a need for a more reactive approach in the development lifecycle. So the idea of self-healing code is to extend that partnership onto the more reactive and operational nature of software development so that we can use things like metrics and logs and traces in order to improve our overall code health and performance. So to make this loop of self-improvement possible or create this system, we're going to need to consider three main components. So the first one is our application logs. So these are the actual logs that are being emitted by our application, and it also includes any error logs and stack traces. We're also going to need the source code system, which is going to be hosting our code, which is quite often going to be Git. And then finally, we're going to need some semblance of a generative AI agent. And I'm using the term agent here in a bit of a broad term to encapsulate both the large language model that's going to perform the code modification, but also the surrounding business logic and code that's going to string everything together. And that agent is going to have to map the application logs back to the source code from where it came from, as well as generate the modified and improved source code, which it can then push back into our source code repositories. So for this demo, we're going to simulate an error that's going to occur for a sample application that we're calling the Orders API. So the Orders API is quite a simple HTTP API that's capable of receiving and triaging product order requests from our users. So in this example, a user can call our Amazon API gateway, make an API call to an Amazon API gateway, which is then going to forward the request onto our AWS Lambda function. So that Lambda function is going to be the main backend for our API. That Lambda function is also going to be integrated with CloudWatch logs. So any of the standard out and standard error logs are going to land in our CloudWatch log group. And then from there, we're going to be selectively taking only the error logs or stack traces that come out of this Lambda function, and then pushing those onto our self-healing code system, which is going to be responsible for creating a bug fix and then generating a pull request that we can review. And I'll take you through the details of what this self-healing code system is in a couple of slides down. But before that, we'll dive into the actual Orders API Lambda function that you can see here and what it's doing. So it's quite simple. It's written in Python. From the top there, what it's doing is it's expecting an event body from our user, and it's going to contain the order items that have been submitted by the user. It's then going to try to generate an UID to identify the actual order that's been created by the user, and then it's going to package both of those things up and then save it in a DynamoDB table. Now, on success of all of those different commands, it's going to, as you would expect, return a 201 status code to indicate that the order has successfully been created in the system, and it's also going to return the order ID as well to identify the order back to the user. So now we're going to flip over to my terminal, where we can make a sample request. If I can type properly. There we go. Okay, so for this, I'm going to be using the curl command line utility in order to make a post request to our API. I'm going to be targeting the API gateway that you just saw there that I already have provisioned in my AWS account and hitting the orders endpoint. And I'm also going to be attaching a JSON payload, the order items, with the order items key included, as is expected by my API. So if I make an API call to this API gateway, I'm expecting a positive response. There we have it, a 201 status code to indicate that the order has in fact successfully been created, as well as the order ID for me as a user to reference for my own records. So that's the happy path to our API. So what I want to do next is show you what happens if, for example, I'm a user that has misread or misunderstood the API documentation, and instead of the order items key, what if I give it the orders key, which is not expected by my API? Then let's see how it's going to react. So in this case, it's responded with a 502 status code indicating that there was a bad gateway response, and also an internal server error indicating that something went wrong on the server side, which in this case is going to be our Lambda function being served behind our API gateway. So this isn't really an ideal response for two big reasons. The first one is that this is clearly a user error that was made on my behalf, and it really shouldn't be an unexpected or transient error on the server end. It should be something that it should be able to handle more gracefully. And then second of all, the error message internal server error isn't particularly helpful for me as a user in order to remediate the actual request as well, so that's going to be successful in future. So there's a little bit of improvement to be made for this API. So if we can go back to the slides again. So in that error that I've just triggered, we can very clearly see that the highlighted text is where the error has actually occurred. So in Python, if you try to access a dictionary key that doesn't exist, then it's immediately going to throw a key error, which is exactly what's occurred in this case for this API. Now, if that happens for a Lambda function that's being served behind an API gateway, like in this example, it's going to return a 502 status code to indicate that there was something wrong on the server end, as well as that generic error message saying there was an internal server error back to the user, which is exactly what we saw. So this is where our system of self-healing code comes into play. So as we speak, if you remember from the previous slides down, we had our self-healing code system wired up to our orders API. So any error messages that occur in our orders API are going to be automatically sent down to our self-healing code system. So as we speak, this self-healing code system hopefully has picked up on that error log and is actively creating a bug fix as well as a pull request for us. So while that's happening, I'm going to walk you through what's actually happening in this cluttered diagram. So starting from the top left corner, you can see the target application, which in this case is going to be our orders API, and that's integrated with our CloudWatch log group. And then from there, I'm using what's called a log subscription filter, which is going to be filtering for specific log entry matches. So in this case, I'm looking literally for the terms stack trace in the log entries. So anytime it finds a match, it's going to invoke the deduplication Lambda function. And the reason I've got a filter there is because I want to decrease the amount of downstream invocation so that I can save on costs in invocation. So that deduplication Lambda function is responsible for, first of all, creating an MD5 hash based on the stack trace that was included in the code, and then we're going to be saving that in a DynamoDB table as the key. And the reason why we're doing that is, again, we want to reduce the amount of downstream processing as much as possible, and we're going to be storing each unique error message or stack trace in our DynamoDB table and only produce a fix once each. So from there, we're using DynamoDB streams, which is effectively a change data capture stream to detect any writes and updates that are made to our table. So anytime that happens, it's going to invoke our second Lambda function, the triaging function. So this triaging function is specifically looking only for new items that are created in our DynamoDB table. And then once it finds it, it's going to push it onto our SQS queue, including the stack trace, and then it's going to execute our main Lambda function for today, which is the AI agent. So this AI agent is going to do the majority of the heavy lifting, where it's going to interact with both the Git repository, which is GitHub in this case, as well as our large language model via the Amazon Bedrock API. So let's go into the details of what's inside this AI agent. So at a glance, this is what it's doing. I'll take you through each of these steps in a little bit more detail later, but at a glance, first of all, it'll clone the source code into its local file system. It's going to then create a prompt, giving it some high-level instructions saying you're a code debugging assistant that needs to fix some code. We're also going to be including the actual source code that's associated with the error, as well as the stack trace that was included in the SQS message. And then we're going to take that prompt and we're going to invoke our Claude v3 large language model via the Amazon Bedrock API. And as part of the response back from the model, we're expecting the actual modified source code that's going to address the bug that we saw. So once we have the response back from the model, we're just going to write those code changes back down to our locally checked out file system on top of the existing source code that we checked out in the first step. And then finally, we can then interact with our usual Git commands to push up the branch, including the new code, and then create a pull request that we can review. So let's go into each of those steps in a little bit more detail. So the first step is to clone our source code. And for this, I'm going to be using the Git Python library, which is a third-party library you can use to interact with your usual Git commands, but you can do it in your Python code base, which suits our need for this one. And we're going to be using the repo class method clone from in order to target a specific URL, which in this case is my code that's hosted in GitHub. And then we're going to provide a repo directory, which is our temporary file system in our Lambda function. And then we're also providing it the SSH private key in order for it to have the right permissions to pull and push the code back. So the next step is for us to put together our prompt. So this is a bit of an abbreviated version of what the prompt actually is, but the idea is that we're giving it some high-level instructions about what it needs to do. So the first thing is we're telling it that it's a code debugging assistant. We're going to tell it that it needs to debug the stack traces that we provide in order to remediate the error from occurring again. And then finally, we're also going to be telling it to modify only the relevant parts of the source code. And that's so that we can reduce the amount of changed source code for any unrelated parts of the code base. So as is best practice, we're also going to be including an example of the response that we're expecting back from the model as well. In this case, we're asking for a JSON formatted response with the keys description and title to describe the actual pull request or the fix that it's producing so that we can use those in different areas later. And then, of course, the actual source code as well, which is going to be an array of different files that have been modified by our large language model. And it's also going to include the file name of the file that was modified, as well as the literal contents of that file as well, returned as part of the output from the model. So at a glance, this is what our overall prompt is going to look like. So just from the top there, again, we're telling it that it's a code debugging assistant. We're giving it the high-level instructions on what it needs to do. We're giving it the example response of what we're expecting back from the model. We're giving it the actual stack trace that came through as part of the SQS message. And that stack trace is going to have a reference back to the actual source code file that invoked the actual exception. And then as part of that, we're also going to be including the source code as well that caused the error. And finally, we're going to be including the beginning of the JSON response structure with the opening curly brackets. And that's so that we can get the large language model to respond back to us in a predictable format, which is JSON format in this case. So now that we have our prompt constructed, all we have to do now is invoke our large language model. So to do that, we're going to be using the LangChain library, which is a framework for interacting with large language models, and it does integrate with Amazon Bedrock as well. So again, an abbreviated version of the code that's actually working under the hood. But what we're doing is instantiating a Bedrock client. We're telling it what model we want it to use, which is Claude v3 in this case. And then we're going to invoke the model using the prompt that we generated from the previous step. And in the response, we're going to be expecting back the modified and improved source code. So once we have the modified source code back from the model, all we have to do now is write the code back to our local file system, literally on top of the cloned source code that we already have. And from there, we can interact with our usual Git commands in order to create a new branch to identify the bug fix, to create a new commit, and we can use the description that was provided back from the large language model as the commit message, and we can push that branch up to our source control system, which is Git in this case. And then finally, we can go ahead and create our pull request against the GitHub API. So we're providing it the title, the description that we got back from the large language model as the title and body, respectively. And we're also giving it the target branch that we created in the previous step as well as the base branch, which is main, where we're going to be merging the source code into. And then we just need to make a post request to the GitHub API using the requests library and including the data that we just created. So I'm going to go back to my screen now. So hopefully by now I've bought enough time for my self-healing code system to have already created my bug fix. So what I'm going to do is refresh my screen, and hopefully there we have it. We have a pull request that was created by our self-healing code system. So if I go into that, let's have a look at what it's come up with. So first of all, the title is Handle Missing Order Items Key, which is exactly what it's doing. We're addressing the fact that the order items key was missing from the body, and we need to handle that. It's also given us a description in a little bit more detail, saying it needs to specifically handle the key error when we access the order items key, which is exactly what we needed to do as well. Most importantly, let's look at the files that have actually been changed as part of this process. So as we can see there, instead of accessing the order items key directly from our body, what we're doing now, what it's suggesting we're doing now, is wrap it in a try except clause. So anytime we access the dictionary, which is the body, and the order items key is missing, it's going to throw a key error, but we're going to catch that in this case, and then respond back to the user indicating an HTTP status code of 400 to indicate there was a bad request made by the user. And then we're also going to be appending a bit of text to indicate that the order items key was missing from the request. So I'm happy with this pull request for 2 reasons. The first one is that you can see here that it definitely understands the context of what this code is, which is an API. So instead of just catching the key error and suppressing it from occurring, it's actually returning back an appropriate response back to the user, indicating that it was a user-based error, a bad request, so an HTTP status code of 400. And it's even providing the user back some guidance, order items missing, so that they can actually remediate that error for themselves and interact with the API in the correct way. So I'm happy with the changes that it's made, so I'm going to go ahead and merge these changes now. Merge pull request, confirm. So those changes are now in our main branch, so all I have to do now is go back to my terminal, and I'm already in the orders API codebase, so I can just do a git pull to pull down the latest changes that have been made to the codebase. And there we have it. And I'm just going to do a git show as well, just to confirm that we have the right commit. And yes, so handle missing order items key, which is the pull request that was just created. So we have the right code. So all we have to do now is go ahead and push that back up to our API to deploy it. And to do that, I've already got a script created, the update code sh file, which is effectively going to go and update the Lambda function on the fly so that we can get a really quick cycle for this demo. So it's going to zip the Lambda function package, push it up to the Lambda service, and wait for it to complete updating, which it has. So effectively, the modified code via courtesy of our large language model is now live in our API. So all I have to do now is pull up the same call request that I had from earlier. Again, I'm still emulating the user who has misread the documentation, and instead of the correct order items key, I'm providing it the orders key. So instead of the 500 response that we got earlier, we're expecting something different. So there we go, 400 status code to indicate that it was in fact a bad request made from me as a user, and with some helpful text to indicate that the order items was indeed missing. So if I wanted to fix this for myself, I would just need to include the order items key in my request. All right, so I'll go back to my slides now. So there we saw an end-to-end system of self-healing code, whereby creating a source code-aware generative AI agent, we were able to stitch together a system of self-healing code. But to be completely honest, that was a very simple use case where the code base was tiny and the error was quite rudimentary and simple to solve as well. And obviously, it's not going to be this simple in real life. We'll still need to address things like the fact that these bugs are going to be more complicated, potentially traversing multiple file systems, multiple code bases, and we're going to have to address that kind of complexity as well for this to be useful. We also need to address token sizes as well. So while the maximum tokens that we can use for our large language models is incrementally increasing, we still want to address the fact that we want to minimize the amount of tokens that we need for our inputs and outputs, both to decrease our costs, but also to address any large code bases that we might be interacting with as well. But despite these existing and open-ended issues, the key takeaway here is that the idea of self-healing code and the next-gen developer experience is already possible today. So if we're able to partner with and embrace generative AI as a coding companion and a coding agent, we have a huge opportunity available to dramatically improve our experience and capabilities as a developer. So the key takeaway for this session is, please experiment, please build with generative AI in the developer experience workspace, and let's find out what's actually possible to build. So if you'd like to learn more about the topics from today, I've got the self-healing code project available in the solutions library with the actual sample code as well as the implementation guidance as well. So please feel free to check that out if you'd like to build your own version of self-healing code. And I've also got a blog link there for Code Whisperer best practices when doing prompt engineering. We also have the skillbuilder.aws available if you want to visit, if you want to get access to our online center for learning with hundreds of different digital courses and gamified learning opportunities. So please feel free to check that out too. Otherwise, thank you for your time today. I hope you got something out of it. Please make sure to check out the survey as well. Thank you.
He will actually be at the back of the room after this session, ready to take on questions. Next up in this room, we have Level 200 session on navigating security in modern app development. Again, if you are leaving, please take your headphones with you and have your badge ready at the door to scan out so we can get in and out quickly. Thank you. Have a great day.